Hi class, we're going to start our next section. It's on dot products and orthogonal sets. In your textbook, it's 6.1. I don't know if you've noticed, but we kind of changed textbooks in the middle of everything. We're going in the same order though, so if you refer to your textbook, there's no difference. Okay, just slightly in the way that we propose things, but I switched textbooks ever since we came in, ever since I started this class, so there's really nothing different, okay? But I am going to start labeling the sections now that we officially have something different using this web assign, and you can refer to that textbook and things like that, okay? So regardless, we're starting on dot products, okay? Dot products and orthogonality. So this, you just finished your exam, right? Your last midterm. So now we're into the last portion of the class. This last month is the last sort of, we're going to start working on the last sections of linear algebra. So everything obviously kind of has to do with what we're doing before, right? Everything, it's like a snowball effect in linear. Everything builds off of everything previous. But now we're going to really get into the nuts and bolts of linear algebra. So we saw before how we could use things like eigenvalues and eigenvectors, and how basis and linear independence was important for solving like things like differential equations. Now we're going to again use a lot of these ideas of bases and vector spaces. Okay, a lot of vector space stuff. So what we're really going to do is we're going to talk about very abstract spaces that are not necessarily vector spaces, but what we call inner product spaces. So the dot product is our first exposure to a certain type of inner product. We're going to expand on this idea of inner products later, but for right now we're just going to talk about the dot product. So the stuff that we do now, we are going to then apply to all the stuff that we've done before so far up to this class, and we're going to really develop the powerful ideas of linear algebra. So really, in a nutshell, the stuff that we're doing now is going to form the basis for things like quantum mechanics, okay? Quantum mechanics, Fourier analysis, all these like high level topics are going to kind of be proposed now, okay? So again, we'll go slowly, we'll work through them, but this is sort of like the entry into the middle upper levels of linear algebra, where you really start to apply these things to abstract ideas, to like more of the physical world, to the more interesting stuff, I would say. Okay, so let's get started, because I've been talking for a while already and we haven't seen anything. So let's just talk about dot products. That's where we need to start. Everything from here on will be a dot product, and then we'll expand that idea of dot product into an inner product in the next couple of sections. I think actually once we finish this chapter, at the end of the whole chapter, not the section but the chapter, we'll start to talk about inner products. So the definition of a dot product is, first we need to have two vectors. Okay, so basically what a dot product is the way that we multiply vectors together. So we're going to have two vectors in Rn, right? That's our general space. It just lets us have a vector of any size, basically. So I have these two vectors, and then I can start to multiply them together. The definition, our easiest definition in dot product, the easiest way to multiply them together is the dot product, which is u dot v. Okay, and we can simplify this into a vector formula as the transpose of u times v. So we take u and we just flip it on its side, and we multiply that times v, because right now if I multiply u and v together, their dimensions don't match up, right? Remember, for a matrix times a matrix, your number of rows here have to match the number of columns here. So if I flip this on its sides, then the number of columns now match the number of rows, and I can multiply it together. So all I really do is I flip this on its side, and I can then multiply them together. Okay, so I transpose u, I multiply it times v, so u1 and v1 multiply, and that adds to u2 times v2, and so forth, which we can write as such. So notice, you guys, okay, I'm multiplying two values. I'm adding that to another multiple of two values. I'm adding a bunch of, so this is a number plus a number plus a number plus a number for n times, right? So if I'm adding a bunch of things up, I'm going to get a number. So the dot product of two vectors is not another vector. The way that we multiply vectors together, it gives us out a scalar value, a number, okay? So I will get a single value here, okay? So if I take an example in R3, very, very standard, right? I take this vector and I want to multiply it by this vector. I'm really just going to multiply their components together and then add that up as a sum, okay? So u dot v is 2 times -1 plus 3 times 2 plus 1 times 0, or -2 plus 6, which should get me 4. Okay, so again, I take a vector times a vector, and I do not get another vector, I get a scalar value. Okay, when I add vectors and subtract them, I get a new vector. When I multiply them, I get a scalar. Now, if we want to multiply vectors and get a new vector, then we take the cross product, which kind of got glanced over in your textbook for some reason, and as I was trying to stay with your textbook and not do things that were outside of that textbook, the cross product really never came up. It really should have came up sometime in the determinants, but we kind of rushed through the determinant section, so we didn't see the cross product. But the cross product is how you multiply a vector times another vector to get another vector. So cross products you should learn in Calculus 3. So if you've taken Calc 3, you've seen cross product before. It has to do with the determinant. You can review that on your own. But for what we're doing, we don't really need to worry about the cross product. We're just going to talk about inner products, which is a dot product. Okay. So that's our first example of a dot product. Okay. So now let's move on to a new theorem, right? So this is pretty easy to do. We're going to do this all the time, by the way. So now we're going to look and kind of extend this idea in these topics. So again, right, note that the dot product of two vectors is a scalar and not another vector. Right, so let's jump into the next theorem. The dot product behaves like multiplication with respect to vector addition. So what do I mean by that? I mean that the properties of dot products are similar to the properties of vector addition. Okay, so that sort of analogy hopefully will help you to remember the way that some of the properties of dot products. I'm going to post a secondary video from 3 blue 1 brown on sort of the geometry of dot products. We're going to go over that geometry in the next video a little bit, but I think that the 3 blue 1 brown videos always help a little bit to visualize things. Okay, so let's go over some of these properties. So I need to have 3 vectors, u, v, and w, size whatever, right? It doesn't matter the size. And I'm going to have a scalar value, which is my value of c here. Okay, so c is the scalar. The boldface obviously are the vectors. If I take the dot product of u times v, that's the same as the dot product of v times u. So it is commutative, right? Commutative. It doesn't matter the order, right? If I had u and v together and then take that dot product with w, remember the dot product gives me a scalar, so this will be a vector, this is a vector, and then when I take their dot product together, I will get a scalar value. That will be the same thing as if I were to have distributed this dot product into my parentheses here, right? So again, I am not adding these and taking the dot product. It's the dot product of this, the dot product of this, and then I add those two dot products together, right? So I get a scalar, I get another scalar, and then I add those two scalars together, right? These two things are equal. So I can add the vectors and then take the dot product, or I can take 2 dot products and add those 2 results together. 3 is if I add a scalar multiple times one of my vectors, one of them, not both of them. It's the same as if I were to have taken the dot product and then multiply that dot product times the scalar. And for the last one, if a vector has the dot product with itself it will always be positive or 0, never negative. Okay. And the only time it's actually going to equal 0 is if the dot product you are taking of itself with is actually a 0 vector. Okay, so a vector being dot product with itself is always positive. It will only be 0 if that vector is the 0 vector. Okay, this is very important as well. So let's go ahead and prove this one. Okay, so what I'm going to do for your classwork is I'm actually going to have you guys prove these other 3. But let's go ahead and prove this last one. So the proof of 4. Okay, I need a vector in Rn because I can't do any of this stuff if I don't have a u vector. So let's start off with this. Okay, I'm going to have a vector in here. I don't need the scalar, so I don't need to use the scalar portion, but I do need to have u, right? So then if I decide to take u times u, okay, using my definition of the dot product from before, looks like this. I can do this another way. I could say, well, u looks like this thing, and then I can actually write it out the long way and say I'm going to do u times the transpose of u and do it the long way and write out this thing, and you know, I can do that. I will actually do that, but I'm trying to keep things a little short here. So I can write it as u transpose u, which will give me this formula, right? So again, I just referred to this formula. That's the definition of the dot product. Okay, I have u. I'm trying to prove this, so I need to have this. What does that look like? It looks like, well, basically each component times itself, which is the same thing as each term squared, which is always positive. I'm adding a bunch of positive things together, so I'm gonna get something that's positive. Okay. I should have probably put here, assume that u is not the 0 vector, then this has to be positive. Okay. So if I assume that this dot product is 0, well, then that means that all the terms in here have to be 0, because again, I have 0 times plus 0 plus 0 plus 0. If these are not 0, I would not get 0 out for the dot product. Okay, so all my terms would be 0, would mean that 0 is the u vector, which I just showed here. Right, so the only way to get this dot product to be 0 is if u is the 0 vector itself. Okay, therefore the dot product of u with itself is 0 if and only if u is 0. End proof. So now let's go on to a definition. We're actually going to do a couple of definitions really quickly because there's lots of very important things that come from this dot product. So u and v are orthogonal, meaning that they form right angles. Another term for orthogonal, if you've never heard orthogonal before, is perpendicular. U and v are perpendicular to each other. From now on, we say orthogonal. Okay, perpendicular is really just meant for angles. Here we're talking about vectors and how they lie in relation to each other. So we call them orthogonal vectors. Okay, so u and v are orthogonal to each other in Rn if the dot product between u and v is equal to 0. Okay, this is a very important sort of definition we have here. We are going to use this all the time. You're going to see me use this like 100 times before this video is over. Okay, very important here. If the dot product is 0, then u and v are orthogonal to each other, meaning they form a right angle when you put them tail to tail. Right, very important. Please remember that. Circle it, put a star around it, hella explanation marks, whatever you need to, but this is an important definition here. Okay, so let's start with an example. We want to determine whether or not the vectors u and v are orthogonal to each other or not. So we're going to take the dot product. Once you do this a couple times, you can see very quickly whether it's true or not. 2 times 2, -2, -1, -2, and 3. Right? You're really just multiplying those pieces together and adding them up. But this is only our second time doing it, so I'll write it out. 2 and 2 is 4. -2, -1 is -2. -2 and 3 is -6. So what do I get? +4, +2, which is 6, and a negative 6, so that's 0. So that means that if I were to graph these in 3 dimensions, they would have a right angle between them. Okay, so they are orthogonal vectors. So the next theorem, okay, if I have a vector, which I'll call x, inside of Rn, so it's it has n terms, then the length of x is called the norm. And this is, again, this is very important too. So everything we're doing right now is the framework for what we're going to do for the rest of the class. So really make sure you try to get a handle on these terms and definitions. Again, we're going to use them a lot, so you'll get more familiar with them as we use them more often, right? So I have a n-termed variable, okay? I would like to know what the length of x is. I'm sure you guys have talked about length of vectors before in your physics or engineering class or even in trig, okay? The difference is that this is in n dimensions and not 2 dimensions or 3 dimensions, okay? So the norm is, this is called the norm of x, and it's just the square root of the dot product. This is an important term here as well. Okay, so we put 2 bars around here. It's almost like absolute value, like the length of x. But in linear algebra, we give it 2 lines, 2 absolute values, like a double nested absolute value, I guess you could say. And it's called the norm, right? So it's the length of x, and it's defined as the square root of x dot product with itself, or the square root of each of the terms squared, right? So you should be familiar with this from, again, from your trig class, right? Or even Calc 3 or any other class where you're using vectors, right? So we call this the norm of the vector. So let's talk about a couple of properties of the norm. If c is a scalar, then c times x, the norm of a scalar multiple of x, is going to be the absolute value of your scalar times your length of x, your norm of x. Again, we're talking about distances here, right? So what we're going to do is we're going to start to apply this norm to a lot of the distance formulas you've probably seen before from regular geometry, algebra, calculus, things like that, okay? So this is, the norm is how we talk about length in vectors and in vector spaces, actually. So I'm just going to kind of go ahead right now, right? The norm is, with the dot product, is how we talked about lengths in your standard vector space, your Rn space, okay? We're going to move into regular inner products, and when we talk about the length or the norm with other inner products, we're going to be talking about length in other function spaces, other vector spaces. So right now, this is like the most basic case. In the next chapter we get to, we're going to talk about length and all these same things, but in terms of, let's say, integrals or derivatives. How do I talk about lengths with integrals and derivatives? How do I talk about length in terms of matrices or polynomials or things like that, right? So right now we're just in the regular Euclidean geometry, the regular geometry you're used to, R2, R3, or whatever kind of stuff, and what length looks like there. So that's just a preview. Don't get too worried about it. We'll definitely be building a lot of skills before we get there. I just want you to kind of know sort of where we're headed to. Okay, so again, this is talking about length in the regular spaces that you're used to, right? R2, R3, R of any size. So if the length of a scalar multiple of a vector is the same as the absolute value of that scalar times the length of the vector. So again, right, if I have a vector, and whether or not I'm multiplying it by a positive or negative value, so changing the direction from positive to negative, it still has the same length. So that's why I need absolute values, square roots, square signs, all that kind of stuff, okay? The norm squared, okay, is the same thing, but me squaring everything. So instead of the square root of the dot product with itself, or the square root of each term squared, okay, I'm going to undo that because I'm squaring everything. So I'm going to get just the dot product, or just all of the terms squared, right? So we use norm squared everywhere, we use norm everywhere. These two are very, very important to understand, right? As well as just your regular dot product. So these three things are really what's going to drive the rest of this section, this video and the next video, right? So these are the main three things to kind of take away from this video, because everything else is how we use these three ideas. And obviously they're very related because the dot product is everywhere. The norm and the norm squared, it's all related, okay? So let's talk about some of the interesting things that we can do with this, which is, again, distance, right? Distance between two vectors. You're just going to subtract two vectors and take the length of the distance between them, right? So this is the function we have for distance. This distance function should have been shown to you in other places, not in this form, but you should have seen this notation somewhere. It's the distance from u to v, or if I subtract u and v, and then I find the distance or the norm between that resultant vector. So again, here's u, here's v. Remember the way that it works. If I subtract this, I can talk about this as the distance between it, or any other the geometric ways that you arrange vectors to take their subtraction, and you're finding the distance between those things. Okay, so if this is u and this is v, this is the distance between u and v. I can rearrange these so that, I don't know, I guess I take u and then I subtract v, and then I add that together and I get my parallelogram rule, and then the length of that resulting vector would be this vector, right? So again, if I were to change directions here and then do my parallelogram, and then that vector I would have across the diagonal of that parallelogram would be this exact same vector, okay? If that's how you remember how to subtract vectors, if not, whatever you need to do, that's fine. But this is what the distance between two vectors is, okay? Next, we have the triangle inequality. So if I add two vectors together, u plus v, again, if I get the parallelogram rule and I get that resultant vector, that will always be less than or equal to the length of u plus the length of v, right? And again, this should be familiar to you. It's saying that the distance between 2 points is always smaller than if I were to go around, basically, right? So if I have a vector, where would that be here? It would be about here. If I want to get here from 0, the fastest way for me to get there is from 0 to that distance. The long way is to go u and then v, right? So the shortest distance is the direct distance between 2 points, u and v. If I add them together with the parallelogram rule, I end up here somewhere, right? So this line u plus v is the fastest way to get there. Going along u and then along v is the long way, okay? The Pythagorean theorem, same thing, it has to do with distance. That the length of u plus v squared is going to be equal to the length of u squared plus v squared, or it could be less than if it's not a right triangle, right? If it is a right triangle, then that means that the dot product between u and v is 0, right? So remember, the Pythagorean theorem for right triangles is always equal, but that would mean that my u and my v are equal, and that distance between them, if I were to add them up, would be equal to 0. Okay, so again, these are things that you should be familiar with from standard geometry, algebra, but applied to vectors. Okay, so the Cauchy-Schwarz inequality means that the absolute value of the dot product is less than or equal to the length of u times the length of v. Notice here that this is a scalar. Dot product is a scalar. The length of a vector is a scalar. The length of another vector is a scalar. So this is a scalar being larger than this scalar. All of these are also scalars as well, right? So it's important to remember when your result is a scalar versus a vector. Whenever I take the length of something, I'm getting a scalar value out. Whenever I take the dot product of something, I'm getting a scalar value out. Let's get to the next theorem. So again, if you notice, I'm trying to go slow here so that we understand what the proposition is before we get into kind of the meat and potatoes. So remember, a theorem is always if and then, right? I got some stuff going. If this works, then some other stuff. Because when we do proofs, we assume that the if stuff is true, and then I have to show that the then part is true. Okay, so we have a vector u that has n components, right? N terms. And let's say that this is orthogonal to a subspace, okay, S of Rn. So S is a subspace. It's a subspace of Rn. So Rn is an n-dimensional space. Maybe this is R2. Maybe this is R3. Maybe it's R10. Maybe it's a subspace that's not a full vector space, okay? So let's kind of start this again. So vector u in R is orthogonal to a subspace. So I have a vector that is orthogonal to an entire subspace, right? And this subspace is a subspace of Rn. If u dot s, so the dot product of u with any vector in S is 0, right? So for every S inside of this subspace. So again, let's think about this again. I actually have a picture to help you out here. If I have a vector, okay, and it is orthogonal, it has a dot product of 0 with every vector that is in a subspace, then that vector is orthogonal to the subspace. Okay, so that's the first part. The set of all orthogonal vectors to S is called the orthogonal complement of S, which is denoted by S to the perpendicular sign. I don't know what you call this, right? We call it the orthogonal complement of S. So the orthogonal complement of S is a subspace of Rn. So this is what we're actually going to prove this, but let's kind of break this down. Okay, so the first part, if there's a vector that is orthogonal to every vector in S, then it is orthogonal to the subspace. If I have a collection of vectors where all of those vectors in that collection are orthogonal to S, then that collection of vectors is called the orthogonal complement. Okay, so let's think about this again, right? One more time. All of the vectors in S, if I have a collection of vectors that are all orthogonal to every vector there, that collection is orthogonal to this. So the easiest way to think about this is, let's think about R3, okay, as my vector space maybe. Let's think about a plane R2 that is in R3, and then let's talk about a second plane in R3 that is perpendicular to that one, right? So think about two perpendicular planes. Every vector in one of those planes is perpendicular to the other plane, right? To all the vectors in the other plane. Okay, so this image right here is just an example of a vector that is orthogonal to every vector in the subspace. So if we're talking about 3 dimensions, if my subspace is R2, some plane, right, in R3, any vector that is orthogonal to that collection of vectors is orthogonal to every vector in that plane, because every vector in S lies in this plane. It doesn't come out of that plane. It lies in that plane. So all the collection of vectors that are orthogonal to this plane make up the orthogonal complement. So you can think of the orthogonal complement as all the planes that are orthogonal to this plane. Okay, that's the easiest way to do that. I was going to post a picture of it, but I really couldn't find one in all the textbooks I was looking through. But the easiest way to think about the orthogonal complement is that you just have a plane, and then you have a perpendicular plane to your given plane, right? So then those two planes are perpendicular to each other. They're both subspaces of R3. That's the most basic case that we could talk about, okay? So let's prove this. Let's have two vectors inside of my orthogonal complement, okay? Because that's what it's telling me I have. Let's have R a scalar, and S is in that subspace of Rn, right? So if the dot product of S, if I have the dot product of U with S, right? So again, U is from that orthogonal complement, S is in here. From the definition of dot products, we know that that's the same as if I were to switch the order. It's equivalent, right? They're commutative. So this is from the complementary, this is from the regular space, so that dot product has to equal 0, right? Not too bad so far, right? Okay. So what that means is that this subspace, this orthogonal subspace, or I'm sorry, this orthogonal space has a 0 vector. So just to let you know, what we're doing here is we're proving that the orthogonal complement is a subspace. Okay, we already know that S is a subspace. We know that the collection of vectors in the orthogonal complement have a dot product of 0 with all of the things in here. So what we need to do is we're going to show that the complement of S is a subspace. So the first thing I have to do is show that the 0 vector, or things go to 0 in that orthogonal complement, and that's obvious because that's by definition, right? So let's talk about closure of addition and scalar multiplication. Remember, we can do this all at once. So if I have a scalar times U plus V, U and V being in that orthogonal complement, and I take the dot product with S because that's what the things in the orthogonal complement do. They dot product with the stuff in S and are equal to 0. So I have to show that this is equal to 0 by expanding it out, right? So if I distribute RU plus RV, okay, times S, we saw from the rules of dot product what happens here. Basically, I get this dot product and I get this dot product also. Okay, so I can distribute the dot products through. So this is also in our definition. So let's just go back a little bit here. Okay, all the way to the beginning. Okay, so what we're doing now is we're using all of these properties. I showed we use this property here. We have definitely used this property, and we've definitely just now used this property. Okay, the constant multiple times the vector with the dot product, adding vectors with the dot product, right? We're using all of these right now to prove this theorem that I have. Okay, so RU.S plus RV.S. So what I get to do is take the dot product and pull out the scalar multiple. And then what are these things? Well, I know that U with S, anything in the complement, dot product with a thing in my subspace is going to be 0. So this is going to be 0 plus 0, right? Or 0. So what does that mean? That means that this thing is equal to this, right? So, and which is going to equal 0. So I'm closed under scalar addition and scalar multiplication. Remember, if I show that this is equal to this equals to whatever it means to be in my spaces, in this case, to be in my subspaces means that the dot products are 0. That means that I'm closed under addition and scalar multiplication. Okay, so that means that this is a subspace because the things in the orthogonal complement dot product to 0 with the things in that subspace. That's what it means to be an element of this orthogonal complement. So if I take these things and I dot product them with things in S, right, that's going to equal this. So I'm having that addition and I'm having scalar multiplication and I'm going to 0. Those are the 3 requirements I need to show that something is a subspace. So again, remember, everything we do before carries over. So hopefully you guys didn't just kind of blah through the subspace stuff because it doesn't go away, right? Same with the vector spaces, same with all these things. All of these properties are going to be used over and over and over again. We're just going to talk about crazier and crazier things with them, right? So what does it mean if I'm closed under addition and scalar multiplication? It means the orthogonal complement is a subspace of Rn. End proof. QED. Okay. So let's go over another definition. Okay. an orthogonal set of vectors, which I'll call V. So V is a set of vectors, right? And all of those vectors, in order to be called an orthogonal set, it means that every vector in V has a dot product of 0 with all of the other vectors in V. Okay, so an orthogonal set means that all of the vectors dot product to 0 with all of the other vectors in that set of vectors. That's what this means. Okay, an orthogonal set of vectors V is a set of vectors such that for all x sub I and x sub j in V, meaning I'm just taking two random vectors in V, will always have a dot product of 0. So all of the vectors that are in here will dot product to 0 if you take any two of them. Okay, that's the definition. So the next theorem is that an orthogonal set of non-zero vectors is linearly independent. Okay, so if vectors are not 0 and they all are orthogonal to each other, basically, right, they all dot product to 0, they're going to be linearly independent with each other, right, which should make sense because they're all forming right angles with each other. Obviously, you can't combine two vectors together and have them be forming right angles, right? So what it means to be linearly dependent basically means that you have a scalar multiple of a vector in there somewhere. Okay, so here's our next theorem. Okay, a basis that is an orthogonal set is called an orthogonal basis, right? So if you have a set of vectors, if they're all orthogonal to each other, then that means that they're linearly independent. So if you have a set of vectors that are linearly independent, it forms a basis. So if you have an orthogonal set, they will be an orthogonal basis, basically from this theorem, right? This theorem leads you straight to this theorem. And in fact, we call that an orthogonal basis, okay? That's what it's called, an orthogonal basis. So our next theorem. Let's say I have a set of vectors. There should have been some curly brackets here. I don't know what happened to them. So if S is a set of vectors, it's an orthogonal basis for a subspace of S. So again, all of these vectors form right angles with each other. If I were to dot product any of these vectors with any of the other ones, they will have a dot product of 0. Okay, they're all linearly independent, so they form a basis for a subspace. In fact, it's an orthogonal basis. Then for every S that is inside of this set can be expressed as a linear combination of those previous vectors. And that's just, again, that's coming straight from this definition. What does it mean to be a basis? A basis means that you can then express any vector as linear combinations of the other vectors in that basis. Okay, but here we can do it in a very special way. So the way that this works is that any of my constant terms, coefficients, is going to be the dot product of this S that I'm trying to find with SI divided by the length of S squared for each of these 1, 2, 3. So if I want to find the constant coefficient of C2, then I'm just going to take that vector S2. I'm going to dot product with the vector S I'm trying to form. I'm going to find the norm squared of that length, and I'm going to do the dot product divided by the norm squared. Again, remember, this is a constant value. This is a scalar. This is a scalar. A scalar over a scalar is a scalar. Okay, so I can find any of my coefficients by using this for this expansion that I want to do. Right, so let's talk about these and do an example. Okay, so what I want to do is I want to determine if U1 being this vector, U2 is this vector, and U and this vector form an orthogonal set or not. Okay, again, if they do form an orthogonal set, then that means by default they are linearly independent, okay, by this theorem. So if this forms a linearly independent set that is orthogonal, it will form an orthogonal basis. And since there's 3 vectors and it's in R3, if these are all orthogonal, then they would form an orthogonal basis for R3. Okay, So I need to check to see if U1, U2, and U3 are all orthogonal to each other. The easiest way to do this is not just by randomly picking and choosing, but take 1 with 2, and then 1 with 3, and then 2 with 3. That way 1 has gone with everything, and then 2 has gone with everything because it's already gone with the 1. So I'll do these two, I'll do these two, and then the only one, I'll do these two, I'll do these two, and then the only one that's left is the 2 and the 3. Okay, so let's do that one at a time. Here I'm going to get 5. Here I'm going to get a positive 3, which is 8. And here I'll get a negative 8. So I got positive 8 and negative 8. That's 0. For 1 and 3, I got a 1 plus a 2 is 3 and a negative 3. So that adds up to 0. For the last one, I got 5. I got a negative 4 and a negative 1. So that's 5 and negative 5. So that is also 0. So these three form an orthogonal basis for R3. Okay, U1, U2, and 3 form an orthogonal set. Since it forms an orthogonal set, they are linearly independent. You can check it, right? Plug it in your calculator, take the determinant. The determinant should be non-zero. So since these are linearly independent and orthogonal, they are an orthogonal basis for R3. All right, so let's move on to an example. That should be the end of the video, before we start the next one. So as an example, let's find a basis for the orthogonal complement for a subspace S, where S is generated by linear combinations of these two vectors. Okay, so what does it mean for me to have to find a basis? So what we want to do is we need to find a basis for the subspace that consists of vectors that are all orthogonal to both of these. So I need to have whatever vectors I have for my basis, they all have to be orthogonal to these two. So what I'm going to do is I'm going to set up an equation to kind of figure this out, right? So I'm going to take a vector, a matrix, okay? I'm going to turn this into a matrix. I'm going to multiply it times some unknown vector, and it needs to go to 0, right? Because remember, the dot product is really just me doing matrix multiplication, right? I turn one vector sideways so that the columns match up with the rows, and then I multiply it together. So if I can turn this into a matrix and multiply it times an unknown vector as it goes to 0, I can then kind of solve that thing and look at it for all the things that map to 0. So it's very, very reminiscent of trying to find the basis for the null space, right? That's what I'm basically doing. I'm taking this, I'm turning this into a vector, and I'm finding the basis for the null space of this. I want to know all of the vectors that go to 0 when I multiply it against this transformation matrix, okay? And the basis for that is going to give me the basis for the orthogonal subspace. So it's very, very similar to the things that we did before. So let's kind of start to set this up. My matrix is consisting of these vectors, S1 dot product U, S2 dot product of U, right? So what does that look like? That's the transpose of S1 times U, transpose of S2 times U. Or I can pull out that U vector, and that needs to go to 0 and give me the 0 vector. Okay, so this is just another way of looking at that same thing now that we have this idea of dot products, right? So S1 and S2 are these vectors that I have here. That's what's making that A. So what I'm going to do is I'm going to transpose that, because the vector that I need U needs to have 3 terms. The only way to multiply this times a 3-term thing is to transpose it, right? So that's also what I got from here, right? This is telling me I need to transpose my matrix of basis vectors for S. I need that to equal 0. So I'm just going to go ahead and I'm going to solve this system. I solve this system basically, right? And then solving the system is going to give me the vectors that form a basis of the things for the null space, for the nullity. Okay, so I set this up as an equation because I can't solve it using the inverses because it's not a square matrix. obviously I'm going to have free variables here, which is what I need in order to find the subspace or the basis of vectors that go to 0. Okay, so I reduce this thing, and it looks like this. Obviously, my free variable is going to be x3 here. So when I solve this, I can solve for x1 and x2, or I guess u1 and u2. Call them x's because that's what I'm used to. Sorry about that, you guys. But u1 is negative 7 u3, and u2 is negative 4 u3. So then this is what that u vector looks like. It's a single vector. Okay, we saw some before where we would have two vectors. In this case, I have just one. So any vector of this form, when I take the dot product with this, will get me to 0. So if I take a scalar multiple of this, basically that's any vector of this form, right? Dot product with either of these will get me to 0 because this is the basis for the null space of these vectors, right? So that's really what we're doing. Okay, so this set is the basis for the orthogonal complement of this set.